I was walking my dog yesterday afternoon, and it was one of those days where the weather just felt wrong. You know that feeling?
Wrong how?
Yeah.
Like, ominous.
Yeah, exactly. It was unseasonably warm, which for late January is always a bit suspicious. But it wasn't a nice warm. It was sticky. The air felt heavy, physically pressing on my temples.
Oh, yeah?
I actually had this low-grade headache, and I remember just looking at the sky and thinking, something is about to happen.
That headache weather is a real thing, by the way.
Yeah.
That's a biological response.
Hmm.
You were likely feeling the barometer dropping.
Yeah.
Your body is basically a walking sensor.
Well, my sensor was right on the money. Because, I don't know, maybe 2 hours later, the sky turns this sort of bruised purple color. The wind just kicks up out of nowhere.
Yep.
I'm talking garbage cans rolling down the street. And the temperature drops 20 degrees in what felt like 30 minutes.
Classic. You went through the wash cycle?
It was so violent, and it got me thinking. We see this on the news all the time. The meteorologist stands there, points to that blue line with the triangles, and just says, cold front coming through.
Right.
And we just, we grab a jacket, we treat it like it's just a wardrobe change.
We do. We think of it as, okay, today is warm, tomorrow is cold.
Yeah.
But we totally ignore that transition period.
Exactly. But what physically hit me, because it felt like I got hit by a truck. And when I started looking into the source material for this deep dive, I realized that in terms of atmospheric fluid dynamics, I kind of did get hit by a truck.
That is a very, very accurate analogy.
Yeah.
A cold front isn't just some line on a map. It is a physical object. It has mass, it has velocity, and it creates a shockwave.
So that is our mission today. We're stepping outside. We are going to decode the physics of the cold front. And I don't want the Weather Channel summary. I want to know what is happening to the air molecules over my head when that blue line crosses my house.
We are absolutely going to get into the weeds. We need to talk about density currents. We're going to define FROPA, which is a great piece of jargon.
I saw that one.
And we're going to talk about why cold fronts are essentially the atmosphere's way of aggressively restoring order.
Aggressive was the word in the research that really stood out to me. This isn't a gentle mixing of air, is it?
Not at all. It's a battle. It's a
Yeah.
plow. If you really want to understand weather, you have to stop thinking of air as this, ethereal, ghostly thing. You have to think of it as a fluid, just like water.
Okay, so let's start with the basics, but then I want to get complicated. When I see that blue line on the map, the one with the little triangles pointing the way, what am I actually looking at? I'm assuming it's not a literal wall of blue air.
No, although that would make forecasting a lot easier. That line represents the leading edge of a cooler, denser air mass that is replacing a warmer air mass. But the key word there is replacing.
Replacing, not just mixing in.
Correct. And this is the fundamental point people get wrong. They think the cold air comes in and just sort of swirls around with warm air until everything is lukewarm. That's not what happens at all.
Okay.
Think about two fluids, like oil and water, or maybe water and syrup. If you pour them into the same container, they don't just instantly blend. They clash. They separate out based on their density.
And that's happening in the sky.
That is exactly what's happening in the sky on a massive scale.
So we have this cold air mass coming down from, I don't know, the Arctic or Canada, and it just crashes into the warm air sitting over us.
Right. And here is the physics aha moment that explains all the violence. Density. Cold air is dense. The molecules are moving slower. They're packed tighter together. It is heavy.
Right.
Warm air is light. It's expansive, and it's energetic.
So the cold air is like a bowling ball, and the warm air is kind of a bag of feathers.
Essentially, yes.
Oh,
That's a
wow.
great way to think about it. So when this cold air mass moves in, it doesn't float. It sinks. It hugs the ground. It moves like a wedge across the surface of the earth.
A wedge.
Like a doorstop.
Exactly like a doorstop. Or, let's go back to your truck analogy. Think of a snowplow.
Okay.
Imagine a snowplow driving down a street filled with slush. The plow is the cold air. The slush is the warm air. The plow doesn't mix with the slush. It stays on the pavement and physically forces the slush up and over it.
And that up and over action, that's the key, isn't it?
That is the engine of the entire storm.
I want to dig into the shape of this wedge for a second, because in the reading, it mentioned that the slope of a cold front is really different from a warm front. The source material used the phrase a steeply sloping boundary. Why is it so steep? Why isn't it just a gentle hill?
That's a great question, and it really comes down to one word.
Friction.
Friction with what? The ground.
Yes. Think about this massive block of cold air sliding south. The air at, say, 5,000 feet is moving along pretty smoothly. But the air that's actually touching the ground,
Mm-hmm.
It's dragging against trees, buildings, hills, forests. It's experiencing drag.
So the feet of the front are kind of getting tripped up.
Exactly. The surface air slows down, but the air above it keeps pushing forward. This causes the nose of the front to bulge forward and get really steep. It creates a very sharp, sometimes almost vertical leading edge.
I saw some ratios in the notes that really put this into perspective. A warm front might have a slope of like 1 to 200.
Right. Which means for every 200 miles you go horizontally, the wedge only rises 1 mile. It's a super gentle ramp. You can barely feel you're going up.
But a cold front.
It can be 1 to 50 or even steeper. It is a wall.
Yeah.
So when that warm air gets hit by the cold front, it doesn't gently glide up a ramp.
It gets kicked.
It gets launched vertically into the atmosphere.
Which explains why the weather happens so fast. I mean, a warm front gives you 2 days of gray skies. A cold front gives you 20 minutes of just chaos.
Precisely. You're compressing all of that lifting energy into a very, very narrow band. And that's why you get thunderstorms, squall lines, and tornadoes instead of just a gentle, boring drizzle.
It's the difference between taking the escalator and being shot out of a cannon.
That is a fantastic analogy, yes. And that cannon shot creates what we call vertical development in the clouds, which we'll get to in a bit. But first, we have to talk about the temperature shock.
Yeah, the numbers here were staggering. We are not talking about needing to put on a light sweater.
No. In strong cold fronts, especially in the transition seasons like spring or fall, you can see temperature drops of 30 degrees Celsius. That's over 50 degrees Fahrenheit.
In what kind of time frame?
Sometimes in just a matter of hours. There are historical records of temperatures dropping 40 or 50 degrees Fahrenheit in minutes during extreme blue norther events in Texas or on the high plains.
That sounds physically dangerous.
Oh, it is. It's a thermodynamic shock wave. I mean, imagine the energy required to cool down the air of an entire state by 30 degrees. It's massive. The atmosphere is expending a huge amount of potential energy trying to equalize that temperature difference.
So when we say the atmosphere is trying to restore balance, this is it in action.
This is it. The atmosphere hates gradients. It hates when one spot is hot and the other is cold. It wants everything to be, gray and lukewarm. A cold front is the atmosphere's most aggressive attempt to fix that imbalance.
It's nature's way of violently mixing the bathtub water.
Very violent mixing.
Okay.
But it takes a lot of energy to move that much heat around.
Okay, so we know what the beast is. It's a dense, steep wedge of cold air acting like a snowplow, dragging its feet on the ground but bullying the warm air up.
Correct.
But what I found so fascinating in the research is that there is a script. There's a timeline to it.
Oh, absolutely.
If you know what to look for, you can see this thing coming hours before it actually hits. It's almost like a horror movie where the music changes before the monster appears.
The atmosphere gives you plenty of hints, if you stop looking at your phone for a minute and just look at the sky.
Let's walk the listener through this timeline. I want to build a FRAPA checklist.
Let's do it.
First off, let's define FRAPA, because I saw this in the notes and I thought it sounded like some kind of fruit drink.
It does sound like a beverage, doesn't it? Can I get a venti fropa? No, it stands for frontal passage. It's the code meteorologists use in their logbooks. They'll write, fropa at 1400 hours. It marks the exact minute the boundary line crosses your station.
I love that. It makes it sound like a tactical event. Prepare for FROPA.
It feels like one. It is absolutely the defining moment of the whole event.
So let's go to phase 1, before the front. This goes back to my walk yesterday, the heaviness. Can you break that down for me? Why did I feel heavy?
You were in what we call the warm sector. That's the wedge of warm air that's about to be displaced. There are 3 things happening to you physically in there. First, the temperature is higher than normal. Second, the dew point is high.
Which means humidity.
Stickiness. The air is just holding a lot of water vapor. But the third thing, and this is the key, is the pressure. The barometer is falling.
Why is it falling? And actually, this confuses me. If cold air is heavy and dense, shouldn't the pressure be rising as it gets closer?
That is a super common point of confusion. The cold air is high pressure, you're right about that,
Yeah.
but it hasn't arrived yet. The cold front is usually trailing from a low pressure center.
Ah.
So as the front approaches, you're actually getting closer to that low. The column of air above your head is weighing less and less.
Okay, so the heaviness I feel in my head is actually the lack of atmospheric weight?
Paradoxically, yes. The heavy feeling is usually the humidity and heat, but the joint pain or the headache, that is your body expanding just slightly because there is less atmospheric pressure pushing down on you.
Hence the old saying, Grandpa's knee is acting up, a storm's coming.
It is scientifically valid. We are basically big bags of fluid, And when the outside pressure drops, we expand.
So we're muggy, it's warm, pressure's dropping. What about the wind? What's it doing?
In the northern hemisphere, the wind is pumping in from the south, southwest or southeast. It's doing everything it can to feed warm, moist air into the system. It's essentially fueling the fire that the cold front is about to ignite.
Then looking up, what are the clouds telling us?
This is where you get your early warning system. Unlike a warm front, which gives you days of warning with thickening stratus clouds, a cold front is faster. You might see some cirrus, those really wispy high clouds. But the real tell, and this is one of my favorite cloud types, is altocumulus.
These are the scales, right?
Yeah.
The mackerel sky.
Yes, exactly. They look like little puffy cotton balls or fish scales, all packed together in rows.
And why do they form? What's that a sign of?
They form in the middle of the atmosphere, maybe 10,000 to 20,000 feet up, and they indicate that the air aloft is becoming unstable. The cold air is actually starting to intrude at high levels before it ever hits the ground.
Wow.
So if you see those thickening up on a muggy afternoon run,
That ominous.
it means the atmosphere is priming itself for an explosion. It means the cap is about to break.
Okay, so the stage is set. We're sweating. The sky looks like fish scales. The wind's blowing from the south. Then, the event, the fruppa.
Moment of impact.
What happens in that specific minute?
It's just chaos. First, the pressure hits its absolute bottom. We'll call that the trough. And then it immediately shoots up. On a graph, it looks like a really sharp V. It bottoms out and then spikes.
The V of violence?
Exactly. And the wind. This is the most obvious sign for anyone standing outside. We call it the shift.
Right. The research mentioned veering and backing. This confused me a little bit. Can we clarify this for everyone listening?
Sure.
Yeah.
It just depends on which hemisphere you're standing in, but the physics is the same. In the northern hemisphere, we look for veering. That means the wind direction changes clockwise.
Clockwise. Okay.
So imagine you're standing on a giant clock face. The wind was blowing from the 7 or 8, that's the southwest. As the front passes, it swings around to the 10 or 11 toward the northwest.
And this isn't a slow rotation over, like, 3 hours.
No. Sudden. It is abrupt. 1 minute the wind is hitting your face, the next it's hitting the back of your head, and it's gusty. This is when you see the trees thrashing, the patio furniture taking flight.
So why does it shift like that? Is it just the cold air pushing it?
It's the change in the pressure gradient. The wind always blows from high pressure to low pressure, but the Coriolis effect curves it. When that pressure trough passes you, the orientation of the isobars, the pressure lines on a map, changes instantly, so the wind just has to realign itself.
And for our listeners in, say, Australia or South America?
For them, it's backing. The wind shifts counterclockwise from northwest to southwest, but the result is exactly the same. Polar air is rushing in to replace equatorial air.
So the wind whips around, the pressure jumps up, and then the temperature crashes.
But the bottom just drops out. And something else happens that people love. The visibility clears up.
Yes, the crispness.
Right. That warm air in the warm sector. It's stagnant. It's full of haze, pollution, pollen. It's just dirty air. The cold air mass coming down from the poles is clean. It's dry. It basically scours out the sky.
So that sparkling blue sky you get the next morning, that's the cold air.
That is high pressure settling in.
But we are skipping the best part. Between the heaviness and the crisp blue sky, there's the drama.
Yes, the rain band.
This is segment 3, the drama. Let's talk about what happens when you launch warm, wet air vertically at, 50 miles per hour.
You get the king of clouds, the cumulonimbus.
Thunderheads.
These are not your friendly little puffy sheet clouds. These are monsters. They can tower 40,000 to 60,000 feet into the atmosphere. They literally hit the top of the troposphere and flatten out like an anvil.
And because the front is a steep wedge, these clouds form in a line, right?
Exactly. A warm front will cover the whole sky in a blanket. A cold front forms a squall line. It's a narrow, incredibly intense band of destruction.
I've seen this on radar. It looks like a red snake slithering across the map.
That's the leading edge. And right under that red line, you have heavy rain, lightning, hail, and if the shear is right, tornadoes.
Shear being the change in wind direction with height.
Right. Remember how we said the wind shifts from southwest to northwest? That turning of the wind creates spin in the atmosphere. And if the updraft from the storm catches that spin, you have a tornado.
It's just terrifying to think that all of this is just physics trying to balance an equation.
It really is. It's just energy transfer. But to us standing underneath it, it feels very personal.
Now, I have to ask a question that came up when I was reading the manual. Does it always rain at the front? Because I feel like I've had cold fronts come through where it just got windy and cold, but there was no storm.
That is a dry passage.
Sounds like a medical condition.
It does. But it just comes down to moisture availability. It's a simple recipe.
Yeah.
You need three things for a thunderstorm.
Yeah.
You need lift, instability, and moisture. The cold front provides the lift.
Check.
The warm air usually provides the instability.
Uh-huh.
But if that warm air is bone dry, maybe it's coming off a desert or it hasn't had time to recharge over the Gulf of Mexico, you can lift it all you want, but you're not going to get condensation.
No water, no cloud.
Exactly.
Yeah.
We'll just get a lot of wind, a sudden freeze, and maybe a lot of dust kicking up.
Which can be dangerous in its own way. I'm thinking fire weather, right?
Absolutely.
Yeah.
Strong winds plus very dry air equals extreme fire danger.
And on the flip side, sometimes the rain doesn't happen at the front, sometimes it happens behind it. The notes mentioned anafronts and catafronts, which sounded way too technical, but can we simplify that?
We can. It's basically about the angle of the flow.
Yeah.
Usually the air rises right at the nose of the front. That's the classic storm. But sometimes the instability is weak and the warm air slides up the back of the cold wedge instead.
So the rain is actually trailing the cold air.
Exactly. You get the wind shift, it gets cold, and then the rain starts. It's usually a cold, miserable rain. And interestingly, as that rain falls into the cold air, it evaporates a little, which cools the air even further.
Evaporative cooling.
Right. It actually reinforces the cold front.
There was one visual phenomenon in the notes that I hadn't heard of before, and I looked up pictures. It's absolutely stunning. Cloud streets.
Ah, yes. These are beautiful.
What are they?
So picture this. The front has passed. The storm is over. The cold air is pouring in behind the front. But sometimes that cold air moves over ground or water that is still pretty warm from the previous few days.
Okay, so cold air over a warm surface.
That heat from the ground starts to bubble up into the cold air. That's convection. But because the wind is blowing so hard and so straight, it organizes those bubbles into these long parallel rows of cumulus clouds.
They look like streets, or like furrows in a freshly plowed field.
Exactly. If you ever look at satellite imagery after a massive cold front sweeps off the east coast of the U.S. over the warm Atlantic Ocean, you'll see these incredible white stripes stretching for hundreds of miles.
That plow analogy really, really holds up.
It really does. If you see those distinct rows of clouds, you're looking at the footprint of the cold air taking control.
So we've covered the anatomy, the timeline, the clouds, and the rain. But I want to zoom out for a minute. Segment 4, the bigger picture. Because these things don't just pop up out of nowhere. They're part of a machine.
The cyclone.
And this is where we get to the really nerdy stuff. I want to talk about frontogenesis and something called the trowel.
The trowel.
Right.
Now we are really diving deep.
Let's start with frontogenesis. It sounds like the prequel to a sci-fi movie.
It does. The genesis of the front.
So how is a front born? Does the atmosphere just decide to make a wall one day?
It's all about tightening the temperature gradient. Imagine you have a blob of warm air and a blob of cold air, but they're far apart. The temperature change between them is gradual. It's a gentle slide.
Okay.
Now imagine the wind pattern aloft. The jet stream starts blowing in a way that pushes those two blobs together. It squeezes them.
Like a deformation zone in geology.
Exactly. It's a deformation field. The winds compress the isotherms, the lines of equal temperature, so the temperature difference occurs over a shorter and shorter distance. That tightening process is frontogenesis. The boundary becomes sharp.
So the wind actually constructs the wall.
Yes. And once that wall is built, a vertical circulation starts. Warm air goes up, cold air goes down. And that circulation becomes self-sustaining. It becomes a weather engine.
So the storm isn't just a side effect, it's the atmosphere expending energy to try and fix the temperature imbalance.
Precisely. It is a heat engine. It's converting potential energy, which is the temperature difference, into kinetic energy, which is wind and storms.
Now, where do these cold fronts usually hang out? The source material mentions something called a dry conveyor belt.
Right. So cold fronts are usually attached to a larger system called an extratropical cyclone. That's just a fancy name for a big low-pressure system in the middle latitudes, like where the U.S. or Europe is.
Okay, can you visualize the swirl for me?
Picture a comma shape on a weather map. The head of the comma is the low-pressure center. The tail of the comma is the cold front.
Got it.
Now, inside that swirl, there are different streams of air, like conveyor belts in a factory. There's a warm conveyor belt bringing moisture up from the south. But wrapping around the backside of the low is the dry conveyor belt.
And where does that air come from?
It comes from way up high, near the stratosphere. It descends. So it's incredibly cold and incredibly dry. The cold front is essentially the leading edge of that dry conveyor belt flow crashing into the warm conveyor belt.
It's amazing to think of it as a 3D structure. We look at the map and we see these 2D lines, but it's actually these huge streams of air wrapping around each other.
It's a complex dance. And because cold fronts move faster than warm fronts, they're actually what eventually kills the storm.
How does that work?
Well, think of it like a race. The warm front is ahead, but it's moving slow. The cold front is behind it, moving fast. Eventually, the cold front catches up.
And this is what we call occlusion.
Yes. When the cold front catches the warm front, it acts like a zipper. It just zips up that whole warm sector.
So what happens to all the warm air?
It has nowhere to go but up. The cold air has completely undercut it, so the warm air is lifted entirely off the ground. It's no longer a wedge at the surface. It's just this pool of warm air floating aloft.
And this leads to my new favorite acronym in all of meteorology, the trowel.
Trowel. Please break that down.
It stands for Trough of Warm Air Aloft.
Exactly. Trough of warm air aloft.
It sounds like a Lord of the Rings location. We must march to the trowel of Mordor.
It describes that tongue of warm air that has been lifted high above the surface because the cold front undercut it completely.
So how would I know if a trowel is over me?
Well, on the surface, it's just cold. The front has passed. But aloft, there's still warm, moist air rising. So you might get heavy snow or rain occurring back in the cold air, wrapped around the system. It's usually a sign that the storm system is maturing and starting to die out.
It's the last gasp of the warm air.
The final breath.
One last thing on the bigger picture seasonality. When should we expect the strongest cold fronts? Because I feel like I see them all year, but the really violent ones seem to be timed.
The transition season, so fall and spring.
Why then? Why not winter when it's the absolute coldest?
Because you need contrast. In the dead of winter, the land is cold, the air is cold. I mean, everything is pretty much cold. The difference between the air masses just isn't as extreme.
And in summer.
In summer, the jet stream retreats way up north. Everything is warm, the fronts are lazy, they stall out, they're not very impressive.
But in spring?
In spring, you still have bitterly cold air pooling in the Arctic, but the sun is waking up the tropics and the Gulf of Mexico. So you have hot, humid air clashing with freezing dry air. That contrast creates the sharpest gradients and therefore the most violent weather.
So the bigger the difference in temperature, the harder the atmosphere fights to fix it.
Exactly. The atmosphere is just trying to reach equilibrium. The further out of whack it is, the harder it snaps back into place.
Okay, let's wrap this up. We have covered a ton of ground here. We've gone from the heaviness of the warm sector to the frappa and all the way to the trawl.
We have indeed.
If you take one thing away from this deep dive, is that the blue line on the map isn't just a drawing. It is a dense, fast-moving wedge of air.
And remember the checklist. If you feel the pressure drop, that headache weather, and you look up and see the altocumulus fish scales in the sky.
And then the wind suddenly shifts from hitting your face to hitting the back of your head.
You have just experienced a frontal passage. You've just been run over by the atmospheric snowplow.
You aren't just getting cold. You are standing in a zone of atmospheric correction.
Exactly.
And I want to leave you with a final thought to chew on. We mentioned that a cold front is just nature trying to balance temperatures. But think about the scale of that.
Go on.
Think about the immense amount of energy that's required to drop the temperature of an entire state. Think of the volume of air over Texas or over France, millions of cubic miles of air to cool that entire mass down by 30 degrees Celsius in just a few hours.
The energy calculation is staggering. It's more energy than entire nuclear arsenals.
We treat it as just weather, maybe grab a sweater, but in reality, a cold front is a massive thermodynamic shock wave that is passing right through us. We are living inside the engine.
That really puts it in perspective. We are very small.
So next time the wind shifts, give a little nod to the physics. Thanks for listening to The Deep Dive. We'll see you next time.
Stay safe out there.